Okay, all set. So I did the following again. I started the package, then I loaded the menu, and now we're here. And so basically these ones here in the model fitting sections are all ones that cover certain aspects of model fitting. The bacteria model is one we just added this year, so it doesn't have the tasks yet. The other ones have been around for a while and have them. If you plan on going through them yourself, you'd want to start with the first one. They kind of build on each other. As you'll see when you go there, in terms of models, you actually won't see anything you haven't already seen. The one new part is that you will now see these models actually being fit to data. And so I'm not going to go through each one in any detail, but I want to give you a few highlights so you get oriented, and then we can take it wherever you want based on your questions. So you see here that model, it's actually simpler than the ones we've seen before. It's the uninfected self, infected self virus, not even an immune response. So that's the whole model that there is. And when you run that, this is just with the default settings. And for those, you usually want to do them on a log plot. So the one thing that's kind of new is you see the data in there. And this is just time series of virus load. It's the average of multiple people that got infected with virus. And in the down here, it will tell you either here or there. What is it? Somewhere it will tell you where the data came from. Basically, I got that from the literature. And it's just, data that was published from a study looking at flu in people. And so here, this walks you through basically, ideally, that almost never happens, but ideally, for each one of these entities you have in your model, you would like to have data, right? You would want to have data on the uninfected cells, the infected cells, and the virus. And then you could fit that all at the same time. Most of the time, you don't have data for all the components in your model, but that's okay because they're all related to each other. If you can fit one of them, it will constrain what the others are doing. So quite often within host studies, we might have data on pathogen load, and we might have data on maybe one or two immune response components or a few. Sometimes we don't have that. So in this case, we didn't have data on uninfected cells and infected cells. Of course, really hard to measure for humans. You could maybe do it for animals, but it's usually unless you have some kind of special, there have been now some technologies where you can basically stain it and then look from the outside with the camera into the animal in mice. But other than that, it would be destructive. You would have to sample and fluid the case, the lungs or the bronchi. So most of it, you can't do that. So you take the data you have, and then basically what you do is you set up your model, you run it for some values of the parameters, and then you change the parameters around with the goal to have your model get as close to the data as possible. So that's in very sort of simple terms what you're doing when you're fitting to a model to the data. And underlying, you use some kind of machinery. It turns out for these kind of models, the underlying machinery is actually a bit more complex than if you might be familiar with fitting linear models or similar models. It's much easier over there. It's more complex here because every time you have to basically run the differential equation underneath, and then you have to compare. The model gives you the whole time series, but of course you only compare here where the data is. So for instance, here day 1 of the data with the day 1 of the model prediction, day 2 of the data with the day 2 of the model prediction, and you look at the difference, and then you change the parameters around to get the difference as small as possible. And then this you consider your best fitting model. So that in a big picture is, how you do it. You can fit a single model to data. What that gives you can get estimates for these parameters. I mentioned before that a lot of these parameters are actually, experimentally not very well defined. If you have the right data, and you can fit a model, you could probably estimate. For instance, you could estimate the rate at which infected cells produce virus. Let's say that little p here. The nice thing about these models is that, if you fit a classic regression model, you have your coefficient B1 or B2 in the model. They don't really have any biological meaning. In our models, all of these parameters have some biological meaning. Sometimes it's a little bit more opaque, like the activation rate of the innate response or something. Sometimes it's more direct, like for instance here, P, the rate of production of virus by infected cells. So just knowing those could actually be useful by itself. Question by Cody, trajectory matching. Yes, that's basically what you're doing here. You're matching a trajectory. So, call it time series, call it trajectory, call it, model curve. All these are the different terms for the same thing. So you have that curve here, and then you kind of try to match it to your data. Of course, the data you only have is discrete times wherever it was sampled. So that's when you do a single model. And that's all I'm going to talk about here. You can, of course, walk yourself through, and we can come back if you have questions about specific ones. Then I'm skipping over the confidence interval, but I'm sure you know that, if you report any kind of result from a model or, even a simple statistical test, you don't just want to report the point estimate, but you also want to report some kind of measures of how uncertain it is or how confident you are in that. And so this second one kind of shows you how you can do that. Not just getting a point estimate for, let's say, the production rate of virus, but also an estimate of uncertainty around it. And the method used here is what's called bootstrapping. Basically, what you do is you take the data you have, you resample the data, and then fit the model to each data sample, and that gives you a measure of uncertainty. So in general, you want to do that when you do these kind of fitting. You want to also have a measure of uncertainty. I'm going to the model comparison because there was a question about that. So, you could fit a single model and it could give you estimates for the parameters, and that's useful. If you want to test different hypotheses, you can implement them in different models and then compare each model to the data. And if one of them fits better, that gives you some support that is maybe the better explanation for the underlying mechanisms. You can never fully prove. But if you have a model that you build that, based on what you think is biologically reasonable, and it absolutely doesn't match the data, you've learned something. You've learned that what you thought was going on is actually not going on. Now, the flip side is not true, because just because your model matches the data well doesn't mean that's naturally right, but it might give you some confidence that you're on the right track. So here, this app does some kind of model comparison here, and it implements two models, uninfected cells, infected cells, virus, and then it has one immune response component, and in one example, we think of it as T cells, and the other one as antibodies. And so they're modeled by different processes. We've looked at it before, and I've showed you a few examples where it's like, well, you can implement these kind of growth and killing and decay mechanisms in different forms. And, often there's more than one reasonable way to do it. If you have data, you could postulate different ones and compare it to the data and then say, okay, this looks more reasonable than this one. So in this case, you have this UIV is very similar. Up here, where we have X, the T cells, they kill the infected cells. Down here, we have X, the B cells or antibodies, and they remove free virus. So different modes of action corresponding to different components of the immune response. And then also assume that they have different kinetics. So here we're assuming that the T cells grow just proportional to the virus load. So it's kind of how they're induced, and then they have an exponential growth. We're not having a decline in this one here because we're thinking acute viral infection, and usually the T cells keep growing after, they don't reach their peak until the infection is already over. Now, if we wanted to model a chronic infection, we would have to change the model. And here for the B cells, I've decided that I model it differently. Really, based on the underlying biology, you could probably use the same model here for both B cells and T cells, because they're in that abstract sense actually rather similar in terms of their kinetics. They both have to be induced, and once they get going, they divide, so they have exponential growth, and eventually they'll die down or level off. But so you have these two models now, and so now you can run each model and compare to data. I'm using the same data set again, so I only have data on the virus here and not anything else. But by fitting the virus and postulating this model, I'm kind of trying to get information about these other immune components, specifically here, the immune response. And, you know, I do log scan again. This is just a run of one model. And right now I'm doing here, model 1. I can change that to model 2. And then I'm running model 2. Now, of course, I'm just taking one step here. Really, when you fit, you need to do it multiple times. So you have to change just iterations here. You need to take a whole lot of steps. And basically, you let the underlying code try to find the best match. And then here, what you see in this app here, it reports the AIC here. We talked about it briefly. So that's one way you can kind of get a goodness of fit estimate. How well does a model fit the data? Now, you should never pick models just on, any statistical criterion. You should always also look at how does it look like. But it might give you some indication if you have several models and they all look visually, reasonable. You could, based on this number, say, okay, one model might fit better than the other. You generally want to report in your paper all the models and how they did. Just picking one and not reporting the others is not that great an idea, because first of all, you learned something by talking about the models that didn't work so well, and also, it's a criterion, it's a statistical criterion, but it might not be right. I mean, it's just kind of a statistical guess of which might be the best model. So unless you need a single model that you take to now go on and make predictions, it's usually good to report the ones you tested. And, also, I mentioned that before, your model should be based on reasonable assumptions about the underlying biology. You could easily make a completely unreasonable, biologically unreasonable model that might produce you a better fit in terms of AIC or any other measure you want. So, just relying on any statistical criterion is not a good approach for any kind of data analysis, not just these kind of models, right? They can be helpers, but you use them together with judgment calls and looking at plots, seeing how well the model predicts the data. Are there any systematic deviations between what the model says and what the data said? Other ways you can maybe enhance your model to make it better. So that's the way you can do model selection with these kind of criteria. But you should, explore the models in enough detail and not just rely on one of those. Also, for those that have some experience, you might know that AIC and BIC, they all weight the data differently. And so, you might find that one AIC says model 1 is best and BIC says model 2 is best. And what do you do, right? I mean, so never trust these kind of measurements blindly. They can be good guiding tools, but you should use your general knowledge. If you have enough data, what you can also do that's becoming more popular and I think is actually the best approach if you can afford it in terms of a lot of data is you're doing cross-validation. That basically means you're fitting your model to part of the data, and then you see how well it predicts the data you didn't use for fitting. And that's sort of a more rigorous test of how well it does. What AIC and similar quantities do, they kind of try to estimate how the model would perform if it saw a new data set. But if you have enough data, you could do it. Now, often we don't have enough data, right? We have here 2, 4, 6, like 8 data points. That's not enough to do anything like that. But if you have enough data, that is something you could do. Let me know if you want to ask more about model comparison. Cody said that statisticians at AIC is too strict, instead prefer BIC. Yeah, no, I mean, people have preferences. Usually BIC is actually more conservative than AIC. But there's no different ones. There's DIC, WAIC, there's a whole bunch. And you can make an argument for one or the other. But again, consider them as tools that can be useful in your toolbox, but don't rely on them too much. There's just one piece of evidence that can be supported. So, you know, fighting over this criterion versus that criterion is really kind of misleading. The other question is also, you know, do you prefer a simpler model versus a more complex model? Maybe for some reason you actually want a simple model because it, you know, you can explore it better, and the complex model might just be overly complex. So there's lots of things that go in, and then of course, if we're going outside of this one, but you know, the more statistical analysis, there's also this whole tension between causal analysis and statistical one. So you might find a model that has a, you know, better performance measured by AIC, but it's actually causally wrong because you didn't formulate it right. So that's less of a risk here because all our models are automatically causal because they are mechanistic models. So we're baking the causes in. But you could easily build a model that makes biologically no sense, but fits the data really well. So feel free to ask questions on that, on the model comparison, especially if you feel like I didn't fully explain it enough yet. And then basically here, this example is applying that, and there's no data here. Do it on a log scan again. This data is a bit more complex because it's now drug treatment, and so you have three sort of arms. One where people didn't get treatment, one where they got the drug early, and one where they got the drug late. And so here the question is, you know, if you have two mechanisms, and we briefly talked about that before, you know, you had one mechanism by which the drug reduced the rate at which cells get infected, or a second mechanism which reduced the rate at which infected cells produced virus. And we postulate that the drug affects either this one, or potentially both or neither. You know, if these are the ones you want to discern, then you could fit it to the data, and maybe by comparing the models, the alternative models, one model with F turned on and no E, and the other model the other way around, it might give you a hint for in which way the drug actually works. Paul talked about that briefly too with the ribavirin drug, where people were curious about what's the mechanism. So here, this is a simple one. This is neuraminidase inhibitor for flu. Can ask a similar question here. So, so there's sort of a applied example, still a toy example, but you can see how you could use this kind of, you know, hypothesis testing. So in this case, your two hypotheses would be the drug works like this. The other one is the drug works like that. Of course, you always have the hypothesis, it's both and it's neither. But, you know, you have your hypotheses, you implement them as models, and then you compare the models to the data, and that might give you some indication which of your hypotheses might be more reasonable or more likely to explain the data compared to others. So that's a major use of these kind of models. And the last one just fits another one, but as I mentioned, this is bacteria data fitting. I haven't fully written the tasks yet, but you can play with it. Here, if you go through them and do the tasks, it basically teaches you in more detail what I just went over fairly briefly, these kind of ideas and concepts. I'm going to stop here real quick and see what kind of questions you have on that conceptually. And then after that, I'm going to peek at a little bit more of the code. Let's see first, did that cover what you had in mind? I think Mui, you asked about model comparison. Some others. Questions, did that cover these? Okay, there's one thumbs up. So Cody asked a question about most fitting tends towards Bayesian. So all of these here that are done in DSIRM are kind of in a frequentist framework. Bayesian is becoming more prevalent. The problem with these kind of models is that it still takes really long. There's a big computational issue still. Because you have to run these underlying ODE models, and for a Bayesian fitting, you have to run them many, many, many times, and that could then take a long time. So there's still just a, computer power hurdle. That's a tricky bit, and then in certain fields, it's also still a matter of Bayesian methods are not that well appreciated yet, but they're definitely growing. So I would say, I don't think they will ever fully replace frequentist methods, but it's definitely a growing area. And while the underlying mechanics are different for Bayesian model fitting, a lot of these topics like model comparison or building alternative models to test different hypotheses, these concepts apply no matter what kind of statistical framework you use to fit your model. It could be a frequentist or it could be a Bayesian one. Okay, keep asking questions in the chat as we go along, and I'm gonna now do a quick switch here and actually show you a little bit more sort of under the hood, some code. Figured that might potentially be useful. So I'm actually gonna start with the ones we just looked at. So here is the basic virus fit, and let me maybe make it a bit bigger. Okay. So again, as you learned earlier, all that stuff at the top is really just for, so when you pull up the help file, you know what's going on. So I'm just going for fitting on the screen, delete really quick. Now this code is getting a bit more complex because it's, it needs to call the underlying differential equation model multiple times, and every time it calls it, it gets the result back, then it needs to compare what the predicted result with the data, and needs to basically keep changing the parameters. So there's, and the parameter changing is its own routine. So there are multiple layers. That's why I'm saying technically this is getting more complex. It's going on. But I'm going to walk you through a bit of the code here. So basically around here is where the main function starts. There's just kinds of some settings. We're loading the data here. We're adjusting it. We're setting the initial conditions. This is just a bit where you can use underlying simulated data or not. I'm going to switch this. And this is really the main call. So this calls an underlying solver. R has several solvers built in. So base R has a package or several solvers called Optim. And they're okay, but for these kind of problems, not that great. And so there's another package in R called NLOptR, which is kind of my favorite, that has all kinds of optimizers. Basically, these are routines that try to get the best match between data and model. And that's actually not a trivial task, because this is a tricky bit fitting. Again, if you had a linear model, that would be a much, much easier computational problem. But for these kind of models, it's actually a difficult computational problem. So you don't want to write this part of the code yourself. You want to use an underlying routine that kind of changes the parameter values around such that it tries to find the best match as quickly as possible. And so this is this line of code here that does the main run. And then you give it the function that it should do. And so this is basically this function up here. And so you feed it the parameter values that it should fit and all kinds of other things that it needs to know. Then what happens is that for everyone here, you call, this should look familiar, the underlying simulate function. So it's a little bit what we did, and when we talked about the level 2, or we did earlier today, where we called the simulate function. So it does so too here inside the fitting. So basically it calls it, then it pulls out the virus values and compares, these are the model predictions, and compares that to the actual data. So the actual data is this here. And here we're doing sum of squares. So if you've done some kind of stats or fitting, that's one way. That's basically, some sense, a frequentist approach. You do the difference between your model prediction and the data squared, and you sum over it. So that's what you're doing here. And then you send it back. And so then what the solver is doing, the optimizer, is it adjusts the parameters that you're fitting. And every time it calls the underlying simulate function again. It gets the time series, the trajectory back. Then it compares that to the data and computes this. And then it keeps changing the parameters. If it changes the parameters in a way that the result, the match, is worse, then it says, okay, that was a bad idea. Let's not go in that direction. And then it changes the parameters in a different direction. And if the fit gets better, then it says, okay, that's good. Let's keep going in that direction. And so it basically searches the space of parameter values to find the optimal fit. That's what's going on underneath. I understand that this is a somewhat more complex, function, because you have multiple layers here, where the underlying model is being called by the optimizer, and the optimizer itself is inside the main function. But I figured I'll show it to you real quick. If you wanted to do that, of course, it would take time to work through a bit. And then here's the same for the model comparison, that function. Again, all that stuff at the top is just the and the reason why I pulled this one up is that here the functions are actually sitting in there, the ODE model. The reason is because I don't actually have an underlying basic app in the package that runs these two models. So there's no simulate underscore for these two models. Now I could have built apps that have those, but I did not. So instead, they're just showing up here. But you see, it looks, again, very familiar that we looked at earlier. So you have that model formulation here for the first model with the du dt. Here I'm having dt before, I just called it du, but you can call it whatever you want. So this is model 1, and here's model 2. And then you have that same thing here. This is the fit function. And then depending on which model you want to fit, it calls this model or that model, gets the result back. And then here, this is that part of the code again that compares the model predicted results with the data and computes the sum of square and returns it back. And the same optimizer as before is doing that repeatedly over and over again to get the best fit. And the call of the optimizer is again, where is it? Here, this one line. It basically calls the optimizer, tells it which function to run and where to start, and then gives you the results back. And really anything that comes underneath is just to basically process the final results and compute the AIC and prepare everything to return to the calling function. But there's just one line of code that does it all. So question. So if you compare fit values to separate outcomes, yeah, as I was saying earlier, what ideally what we would want in these models is if we had data for each one of our components, right? So here, in my case, I only have data for the virus, but if I could, I would want data for all of these. And then what I would do in the code is basically I would compute a big thing here like this sum of square, where I do prediction for the virus load from the model with the measured virus load, plus the prediction of the infected cells from the model and the difference to the measured infected cells, and so on. Now, the one thing I need to think about is that, they might be measured in different units, so I can't just add them up. Otherwise, I would be adding apples and oranges. So what you might want to do is you might divide by the standard deviation. This way you kind of normalize it, and this way every component gets the same weight. But that's how you would do it. You would basically just build one big sum of squares that has all the different parts that you have. And that's, of course, preferred. You would want to do that if you could, because if you have more data, you get more accurate fits out of it. Most of the time, you will only have data on some of the components of your model. Of course, you need it on at least one, but if you can have more, then yes, that's a good thing to do. I want you to, at the same time from this workshop, take away that these are really useful models for certain questions, but also at the same time that these models can't be applied to just anything, right? I mean, there needs to be a match between the tool you're using, in this case, a statistical model, the simulation model, the whatnot, and the setup and the question, right? You need to find the right tool for the right job, right? Now, most people that are trained in the bench sciences, their only tool is a t-test, or some basic stats, and so then they solve everything with that. So hopefully this is extends your repertoire, but definitely the other approach is also not right. Not everything needs to be solved with a mechanistic model, right? There's certain questions where this is the right tool, and then there are others where other tools might be the better ones to use. So, with experience and expanding your tool set, you'll get better at saying, okay, this is the tool I need for this one. And even if you're just at the level where you know what tool to use, but you don't feel fully comfortable doing it, I think it will still put you ahead of a lot of people, because then you can go to someone and say, hey, this is the question I want to answer, this is the system I have. I think we should apply this kind of tool. I know you know how to do it. Can you do it? I think Paul is really good at that, because he works with a lot of people, not just me, but other quantitative people that can do all that stuff, but he understands enough to know which tool to use for which question. So when he does his T-cell repertoires, he doesn't use these mechanistic models, but he still uses sophisticated mathematical statistical models. So, the more you know about the different tools and their pluses and minuses, the better you'll get, even if you're not the one doing it. Any other fitting questions? Question about what strategies minimize your coding mistakes. Yeah, so to me, the best strategy is the one that I've been mentioning multiple times. Start simple, and sort of, even if you start building a big model, turn off half of your model and explore the parts that are easy to explore, and make sure that part works. If you have like a component of cells being born and dying, turn off the infection and just let this part run and make sure it works. Then turn on one of the immune response components and make it do crazy things, like setting parameters to 0 or to some really high value where you know what you should be getting, because you know what then do that one, and then make sure you're getting what you know you should be getting. And then slowly, sort of step by step, turn on certain components, turn them off again, turn others on, turn them off again. And then once you're comfortable, so sort of every sort of component of your model behaves the way it should, I think that's how you can, figure out or build confidence in your model. If you immediately build a big model and you turn everything on and set everything to the values you think are realistic, then it might run and you might get something, but there might still be coding mistakes. You don't even catch it. So I think it's, go slow and try extremes. Parameter values that are 0 or that are 10 to the 10, extremes are often very useful, because you know what you should be getting, right? If you say, I set the death rate of my T cells to 0, then you know that the only thing for the T cell curve that should happen is go up. It should not go down anywhere, because you said there's no removal or death of the T cells. If they do anyway, then something isn't going right. So that's my best recommendation. Start simple and test each component. Yeah, I know the suggestion. Others look at your Codo results. That's definitely, if you have that opportunity, that is definitely a great thing to do. Some people do the team coding. I know there are some research groups who always, their second person reviews the code of the first person. It's called code review. In any kind of software company, that's standard. That's always done. Maybe even more than one person does code review. It's more time consuming. It's more labor intensive. But definitely, if that's an option, I would go for that. And it forces you to put comments in your code and to write clean enough code that another person can actually understand it. And it's good because the more comment. That's another thing. Another recommendations for minimizing coding mistakes: don't try to be clever. And by that, I mean, if you do a very complicated operation by shoving 10 commands into each other and that does something smart, you might be excited now. And when you come back a week later, look at your code, it's like, what in the world did I do there? I have no idea what happened there. And so, it's often sometimes better to make it more pedestrian, step by step. And then, you see here, I have like at least one line of comments for each line of code, sometimes even more. I don't just do that for stuff that I develop for teaching, but I try to do that and get my students to do it too, and research that they write comments. It very much helps for other people to read it, and especially nowadays when you write papers more and more, it's common in journals request that you put all your code and your additional information as part of the paper. And so readers might want to rerun your code and reproduce your results, and then having comments in there is really important. So yeah, comment, write clean code. It doesn't have to be like computer science type code, but write code that makes sense, that it's not too complex. And yeah, those are recommendations. Yeah, lack of labor, that's definitely, and especially if you're in a wet lab and you're the one person who picked up coding and you're doing it and none of your colleagues knows how to do it. But even in computational groups, it takes more time. I've started doing that now, but I have basically one student reproduce the results of another student. It takes more time. I'm hoping that both will learn from that, so it's not wasted time, but it takes more time. But definitely, I mean, it's practice in industry. I'm actually currently formally on a sabbatical with a company, and they are doing consulting projects for pharma, and all of this is analysis of data for clinical trials, getting mostly towards FDA approval. And every project they do quality control, and one person reviews the code of the other person. So it's very standard. I'll start with that real quick, not because I really want to go over it, but I want to contrast it to another one. So this is the bacteria model. This is now one simpler that we earlier saw. Earlier we had the bacteria and the two immune responses, innate and adaptive. This is actually the one simpler one that only has one immune response. So should be somewhat familiar from what we looked at earlier. So, again, the whole thing is this is the whole code here, these few lines of code. That's it. So, this defines your model here. And then this is the call to that DE-solve package with the function ODE that actually runs it. And the reason why I want to pull that up is because I want to contrast it. I briefly mentioned, but we didn't really talk about it, that you can also run these models in discrete time, which is less common, but especially when you do agent-based models, that's basically what you have to do. In some sense, it's simpler because you don't need an underlying package like DE-solve and running an ODE one. Instead, what you do is you're just stepping in through time. In this case here, I just have a for loop. So what happens is you start out with some value, and then every time you update this quantity here, the B's and the I's, based on the processes that can happen, the growth and the decays. So here's this one, and then you just save that as you go along. And here it's saved in that time series data frame. And then you end up with the same, more or less, structure. You have a data frame where you have the columns are your variables and the rows are at each time step. So for these kind of compartmental models that we looked at, ODEs are by far the most common way, but sometimes you might want a discrete time model. And again, especially if you start working on things like agent-based model, they're all running in discrete time. So you will have something equivalent like that. You will have one big loop that steps over the time from whenever you want you start your simulation to the end of your simulation. And inside that, you update whatever you're updating, in discrete time steps. So, if you had a population level model, you're susceptible, in fact, that recovered people would update based on the processes that are allowed. So that would be a discrete version. And then there's no stochastic version for the bacteria model, but there is one for the virus model. And since we briefly talked about the stochastic one, I figured I'd put it up here as well. So you see here that instead of calling the ODE function from the ODE package, I'm here calling the adaptive tau function from the adaptive tau package. So again, I use another package and it does the work for me. It writes the things that are going on underneath. It also wants the function in a certain way, but it looks slightly differently. So this is here the function. It actually in some sense looks even simpler. You just have what's now called rates. These are basically the things that can happen. So in this case, a virus a cell can become infected, and the infected cell can die, and the virus particle can be removed. And then here you specify the transitions. Basically, usually it's always, most of the time, it's plus or minus 1. Occasionally you might have it, at least in chemistry, where these kind of things actually came from originally. You might have different molecules meeting each other and then, creating 2. But in our case, it's, 1 or minus 1. So, for instance, here in the first process, which is the infection process, the infected cells increase by 1 and the uninfected cells decrease by 1. So it takes a little bit reading through the help file of the adaptive tau package to figure out how to formulate it as a stochastic model, but not that much. And then once you have it, you can run this as a stochastic model. And that's, what's running underneath. We saw earlier when I pulled it up and showed you the stochastic one. So this is basically what's been run underneath. So if you have a need for a stochastic model, it's not that much harder. It's computationally because you have to run it more than once now to get samples, but otherwise not that difficult. And then I want to look at one more. And this is basically showing you an example that's under the hood, similar of what we did yesterday when we wrote that little for loop. So I'll do this one here. Yeah. So this is one of the apps, the model exploration. And this all basically is a bit extra because you pick different things that you want to run and simulate. And then underneath, again, it just runs the model. And so here's basically the loop. Remember yesterday we looped over some parameter, KT or something, and we did a certain number. And now here, because you can pick in the app which one you want to loop over, there's this extra thing here that switches. But then basically you run the underlying model here, looping over whichever one you chose. So you see all of the ones are fixed, but whatever one you picked is being adjusted here. So for instance, G or P. And then at the end of the run, it records whatever you might want to record. Like here, for instance, the last one, final value. And then it returns that at the end. So that's very similar to what we did by hand. It has a little bit more bits and pieces because it lets you choose which parameter you want to vary, and it will give you stuff out that you can then plot. But if you play with these apps here, the bacteria model exploration and the virus model exploration, you will see that they're basically doing this thing. So if I run it, you see there's a parameter here that was varied, in this case n, and then we plot some outcome on the y-axis. Similar plots we did yesterday, just manually ourselves. So it's here for those two apps, but you've learned now how you can do it for any of them, underlying one. And combined with what we did earlier today, where we changed the underlying model, you can now combine what we did yesterday, where you write that little loop over a parameter, and you have the underlying model that is the one you want, and then you can start exploring stuff that's pretty realistic, maybe close to getting to research questions. Oh yeah, so the question that goes to what we've what I've mentioned multiple times, you can often build the parts in the model in different ways. Like we looked in the acute virus model here, and I decided to model the innate and the adaptive response in these specific forms. And then we looked at the chronic one, and then I modeled it slightly differently. And the question is, what's the right way of doing it? Unfortunately, the answer is there's not one right way. And also, it kind of depends, and you have some certain freedom there to do it. So that's where, again, that idea that you should try to understand the system well enough that you might have an idea of, okay, this is how this compartment of the immune response is activated. It's most likely that we know T cells and B cells, they grow exponentially because they, divide. So then we should probably model it in that form. And we know that, the way to get these cells activated is best modeled in this form or that form. That said, since we're all already always making abstractions here, there's really not one way to do it. And it's that's a bit where the art of modeling comes in, that there's not one recipe that says always do it this way. That's sometimes left up to you. And the more you know about the system you want to model, the more likely is that the way you do it is a reasonable way of doing it.